残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話にな
Okay, everyone, we're back talking about section 4.7, L'Hôpital's Rule. And I know that's a little bit of a weird spelling right there. Seems a little bit strange, not that hard to pronounce. It's not L Hospitals or something like that. It's L'Hôpital's, L'Hôpital's Rule. So, the basic gist of what's going on is that back in section 2, when we started talking about limits, we went pretty far. We were thorough, but we were not exhaustive. There is still stuff that we have yet to talk about. So at first this section is going to seem like a little bit of an oddball because, out of nowhere we're just going back to limits. It ultimately does fit in. I promise it does. But for the moment, we're just going to jump right into it sort of unmotivated. So the gist of it is, as I'm sure many of you remember from deductions on your quizzes and stuff like that, when you got 0 over 0 out of a limit, this was not a number. This is an indeterminate form. Not a number, not an answer. Just an indeterminate form. So, when we were dealing with these guys, these indeterminate forms, usually, and this is kind of deceptive, but we did it just for simplicity back then, usually when you encountered one of these bad boys, all it meant was that you had to do some factoring. If you were dealing with a rational function, you had to factor a polynomial, cancel something out. But for things other than polynomials, very frequently this doesn't work too well. Also, factoring polynomials is kind of hard. So we can deal with this, as it turns out, a different way. These limits are actually way more interesting, and there's something kind of cool that happens here. And the result we're going to use is called L'Hôpital's Rule. This will let us evaluate this type of indeterminate form as well as some others. There is more than one type of indeterminate form. It's not just this bad boy right here. There are other ones. So we'll start with this one though. And we'll be able to evaluate them with, as you might say, relative ease, though that's the mathematician's easy, not necessarily the colloquial form of easy. It is possible to do this. It is not necessarily easy. This is often one of the sections people struggle with a little bit more, but hopefully we can go through it and convince you it's not too bad. It's not necessarily always super simple, but the process is easy. So without further ado, let's talk about the first instantiation of L'Hôpital's rule. The gist of it is that we've got two functions, f and g, both differentiable on an open interval I containing a point A, with g prime of x not equal to 0 on all of I except potentially at A itself. If both the limit as x goes to A of f and g are 0, Oops. Then, and this is kind of cool, the limit as x goes to a of f over g is the same as the limit as x goes to a of f prime over g prime. This is saying that the limit of a ratio of two functions is the same as the limit of the ratio of their derivatives. It's saying that the ratio of the functions approaches the same value as the ratio of the slopes of their tangent lines. That's totally non-intuitive. That's as weirdly complicated as it sounds right away. So this part right here, this is pretty neat. Now notice, there are a few different things right here we need to have our function satisfy to be able to say this. There are some technicalities we have to deal with. But when it is satisfied, this is weird. This is unusual. Just off the top of your head, it doesn't seem like this has to be the case. But it is true, provided, of course, that this limit actually exists, or is plus or minus infinity if we're analyzing something like that, if we're classifying the way it doesn't exist. As long as you get something other than an indeterminate form, or, just non-existence for some other reason, things like, jump discontinuities, stuff like that, you can actually relate the limit of a ratio of derivatives to the limit of a ratio of functions. It's kind of cool. And of course, this also applies if x goes to a is replaced with x goes to infinity minus infinity, x goes to a from one side, x goes to a from the other side, everything you'd expect. If it works for the two-handed limit, then it sure as heck better work for each of these one-sided limits. And if it works just as you go towards a point, then it should work as you go towards plus or minus infinity, since that's sort of like going towards, increasingly larger points. So if it works for any point, then it should work for a sequence of increasingly large and positive or increasingly large and negative points. Fair enough. So this is weird. We're going to learn about it. Let's get into it. Okay, here we are, guys, back with an example, example 19. We're going to evaluate the limit as x goes to 1 of the function x cubed plus x squared minus 2x over x minus 1. So, notice that if I plug in x equals 1, then I'll get 1 to the third plus 1 squared minus 2 times 1 all over 1 minus 1. Just rolling on through, this is 1 plus 1 minus 2 over 1 minus 1. That is 0 over 0. And what I should be careful here is that that's not equal. Those are equals in little quotation marks. It's not equal. But I'm saying that if you just naively try to plug in the number down there, that x equals 1, into the function right here, you get out something that's nonsense. 0 over 0 doesn't make any sense. It's not a real number. Okay, so 0 over 0, no good. We can't just directly plug things in. Now, if we were back in the earlier sections, what we might do is we might notice that x to the third plus x squared minus 2x, we can factor an x out of everything and turn this into x squared plus x minus 2. That seems fine, right? Okay. And we might notice that this is x times x minus 1 times the quantity, say, x plus 2. Yeah, that's right. Okay, and then we would use this to do a little bit of cancellation. That is, we would go, oh, okay, the limit as x goes to 1 of x to the third plus x squared minus 2x over x minus 1, that this is just the limit as x goes to 1 of this bad boy right there over x minus 1, which, if you're fine with me skipping a quick step, is just gonna be x times x plus 2, since we're gonna have this x minus 1 cancel with that x minus 1, right? I'm gonna uncross those so we don't get confused. But then we'd just plug things in. We'd see we get 1 times 1 plus 2, and we all know that's just 3. Okay, so this is how we would have done it back in chapter 2, But now let's do it with L'Hopital's rule. Let's do it quick and make sure that this actually does work. So since we got the indeterminate form of 0 over 0, we can apply L'Hopital's rule just because, and this is the important piece, we have to be a little careful here, both the function on the top and on the bottom, both these guys are differentiable. They can be derived. And because this bottom guy, x minus 1, has a non-zero derivative everywhere. The derivative is just 1. So it's non-zero, and I can use L'Hopital's rule. So, taking f to be the function x cubed plus x squared minus 2x, and g to be the function x minus 1, we'll get that f prime of x is, well, just 3x squared plus 2x minus 2, just this guy right there, and naturally g prime of x, like we just said, is just 1. So take in this limit, this step right here, this equals, that's L'Hopital's rule in action. L'Hopital's rule in action gives us this equal sign. It says this guy's the same as that guy. Okay, cool. So taking this limit is a lot easier. It's just over 1. So the limit as x goes to 1 of a polynomial. We can plug it in. 3 times 1 squared plus 2 times 1 minus 2, just 3 times 1 squared. No, 3. Same thing we got before. So it works. Or at least it works for this example. You'll have to take my word that it works in general, or go on Wikipedia or in your textbook and read the proof. But at least when we tried a random example, it did indeed work. So, cool. Oftentimes, it is a lot easier to derive things than it is to factor things. Factoring stuff can be difficult, so this is a very convenient fact. All right, let's do some more. Okay, here we are back with another example, example 20. We're going to evaluate the limit as x goes to 0 of the function given by the square root of the quantity 9 plus 3x minus 3 over x. So this guy is going to be another L'Hopital's rule situation. You can already guess it since that's what we're doing. If we try to throw in x equals 0 when we're computing this limit, what we're going to get is we're going to get the square root of 9 plus, it's a little messy right there. Let me get that a little bit cleaner. Square root of 9 plus 3 times 0 minus 3 over 0. We're already running into problems because of that 0 on the bottom. But the next thing we're going to do is just evaluate. 9 plus 3 times 0, just 9. Square root of 9 is 3, so 3 minus 3 over 0. Oh no! Once again, quotation equals marks equals, not really equals, 0 over 0. Bad. This is an indeterminate form. We can't just directly substitute. We got to do something else. So, if we're doing something else, let's use L'Hopital's rule. A lot easier. As you can see right here, it doesn't seem immediately obvious how I might go about factoring this bad boy out. That is, this is not a nice polynomial function. We could maybe turn it into something that looks like one with some nice substitutions or something like that, but overall, this doesn't seem to be nearly as good of a situation. This seems to be a lot more difficult than the polynomial stuff. So this kind of motivates why we even bother with L'Hopital's rule. So let's just notice, let's take care of the technicalities. What do we need to apply L'Hopital's rule? We need both the top and the bottom function to be differentiable, and we need the bottom function to have a non-zero derivative everywhere on some interval around the point we're approaching, except potentially at that point. So we can pretty easily see that the bottom function, let's call it g, let's say g of x is x, and the top function, let's call it f of x is the square root of 9 plus 3x minus 3. If we look, we can pretty easily see that g prime of x is 1. So the derivative of the bottom function, non-zero everywhere, even at 0. Nice, okay. The top function, Still seems differentiable. Now, we get this bad boy out when we take a derivative, just because, as we might notice, we can rewrite f of x, which is, just from up here, this is 9 plus 3x inside of a square root, then minus 3. We could rewrite this as 9 plus 3x to the 1/2 minus 3. And then with a quick application of the chain rule, we can get that f prime of x is equal to, well, just derive this outside guy, 1/2, leave the inside alone, 9 plus 3x to the minus 1/2, that's 1/2 minus 1. And then we just multiply by the derivative of the inside thing there. So that's multiplied by 3. And this gives us 3, and using the fact that that exponent is negative, this is 3 over 2 times the square root of 9 plus 3x. If I can get that a little bit cleaner, I probably ought to. There we go. Something like that. So 3 over 2 times the square root of 9 plus 3x, that's what we get for f prime. Now, we should be a little bit careful here. We should be sure that f is actually differentiable, able to be derived on an open interval containing 0 if we want to satisfy the conditions of L'Hopital's rule. That is, we should just be careful that we can actually plug in numbers close to 0 on either side. It doesn't matter if outside of some radius we can't plug in numbers past that. We just have to be able to plug everything sort of close to 0 in, where close means at least a little bit of a ways away. So the gist here is that if we notice this bottom part, 9 plus 3x, notice 9 plus 3x, if that guy, here, I'll go less than 0. This is when we get some problems. If 9 plus 3x was less than 0, then we'd be getting some negative numbers inside of a square root, which in terms of real valued functions, no. So notice this would just give us, if we solve it, that 3x is less than negative 9, which tells us that x has to be less than what? Minus 9 over 3, so something like minus 3, yeah? So if we're looking at a number line real quick, just to visualize what we're checking for here, here's 0, here's minus 3, and I can put in anything bigger than 0, that's for sure, right? Here's where we're actually able to take a derivative and get something out that makes some sense. From that part all the way on over forever. So the open interval from minus 3 to infinity, this guy is an open interval that contains 0. It's right there, or at least it's right there, just like we drew it. So this function, f, is differentiable on an interval containing 0. G also is, that's fine. We don't even have to worry. G is just a constant function. It's definitely differentiable. But we've satisfied the conditions of L'Hopital's rule. So we can apply it. And we'll just go ahead and throw the derivatives we calculated right on in. So we start with the limit we had at the beginning, this first equal sign. This is, once again, just L'Hopital's rule in action. And applying L'Hopital's rule, we replace each function with its derivative, put f prime on the top, put g prime on the bottom, and if you plug in 0, well, since it's over 1, we're just really plugging it into this top part right here, and 3 over 2 times the square root of 9 plus 3 times 0, well, that's just 3 over 2 times 3. Which we can all do the basic arithmetic, is 1 over 2. So, bada bing, there's our answer. The limit is equal to 1/2. We just dealt with an indeterminate form that we would never have been able to handle using the things we had from Chapter 2. Pretty cool. All right, let's go a little bit further. Let's see what we can find. Okay guys, here we are back at it again with another L'Hopital's rule problem. we're going to evaluate the limit as x goes to 0 of e to the x minus 1 all over x squared. This is going to be one of the first trickier situations. Trickier in quotation marks. It's not really any trickier, but it at least takes one more step. So as you can imagine, this is a L'Hopital's rule situation. Try plugging in 0. You'll get, oh, wrong color. You'll get e to the 0 minus 1 over 0 squared, and that's 1 minus 0 minus 1 over 0 squared. 0 over 0. Oh no. And once again, that equals is in quotation marks. Not really equals. This is just a bad situation overall right here. We can't conclude anything from this crap. All right. So we have to turn to L'Hopital's rule. We should always double check that we can actually deal with these functions, that they satisfy the technicalities we need. We need both of these guys to be differentiable in the appropriate places, and we need the derivative to be non-zero on some interval about 0, except potentially at 0 itself. The only places that the bottom function's derivative can go wrong is at that limiting value. Okay, so we get the indeterminate form 0 over 0, and we try direct substitution. Shucks, not an easy one. We have to do some more. We'll have to apply L'Hopital's rule. We can, since the derivative of the bottom function is 2x, and 2x is not 0 except at x equals 0, and just looking at the top and the bottom function, it's super clear that both those guys are differentiable. E to the x, I can derive that all I want. The rest of it's just a polynomial. The bottom's just a polynomial. I can derive those all I need. So we're good. We can apply L'Hopital's rule. And don't worry, it seems like a lot to check. After a little while, you'll just get used to it and go, oh, yeah, L'Hopital's. I don't even need to check. I'm already familiar with the type of stuff I'll need. So we go through and we apply it. We derive e to the x minus 1, which gives us e to the x minus 1. And we derive x squared, which gives us 2x. This equal sign, once again, that's L'Hopital's in action. L'Hopital's rule helping us out yet again. And I'll skip over doing those derivatives in any depth, just because both those, pretty easy. We can do the power rule, and we know that e to the x derives to e to the x. So there we go. We got this limit. Okay, except now, let's try plugging in x as 0. Oh no, e to the 0 minus 1 over 2 times 0? That's 1 minus 1 over 0. That's 0 over 0. Once again, equals in quotations, equals, not really equals. This is still bad. We need to use L'Hopital's rule again. Now we can definitely use it again, just checking out our function on the top, e to the x minus 1, still differentiable. Bottom function, 2x, still differentiable. I'll just get out 2 when I take a derivative, and that's non-zero at 0, and it's non-zero everywhere near 0. We're good. So, applying L'Hopital's rule yet again, this is one more application of our boy, L'Hopital. Okay, so take a derivative on the top, e to the x minus 1 derives to e to the x. Take a derivative on the bottom, 2x derives to 2. And what do we get when we plug in 0? We get e to the 0 over 2. That's 1 over 2. Hey, bada boom. We've answered our question. That is, we just, in a compact form, wrote that the limit as x goes to 0 of e to the x minus 1 over x squared, that this is equal to, using one application of L'Hopital's, that's equal to the limit as x goes to 0 of e to the x minus 1 over 2x, using yet another application of L'Hopital's, that's the limit as x goes to 0 of e to the x over 2, and now, because we can just directly substitute, I'll get 1 over 2. And hey, this thing equals that, equals that, equals that. This guy equals this guy. Bada bam. We're done. We've solved the problem. Now, it is very easy to overlook a crucial step in this. After we applied L'Hopital's rule the first time, we truly must, like absolutely have to, establish that the new limit we got is still an indeterminate form. That is, if we didn't get 0 over 0 after doing it once, if this guy didn't give us 0 over 0 like we wrote right over here, we could not apply L'Hopital's rule. Otherwise, we'd end up with some silly stuff. Think about, for example, the limit as x goes to 0 of x over x. We could apply L'Hopital's rule to that. That's all good. And we'll get the limit as x goes to 0 of 1 over 1, right? Okay, pretty straightforward. And if we were doing things correctly, we could very easily see that the answer is 1. But if we messed up and tried to apply L'Hopital's rule to this thing, which is not a valid thing to do because you don't get 0 over 0 when you try to plug in 0 for x. If we try to do L'Hopital's rule again, oh no, look what we've gotten. If we derive the top function, that's 0. Derive the bottom function, that's 0. Oh no, oh no. Very bad. No. Never. So be careful on that one. Make sure that you actually are in a situation where it is sensible to use L'Hopital's rule before you just do. If you just keep deriving mindlessly without thinking about what you're doing, it's not going to go well. I mean, pretty much nothing does when you just keep doing it for no reason without thinking. Always be conscious of why you're doing something, and in all likelihood, it's not going to be too bad. So you just got to check that you get 0 over 0, and if you do, and you should really check the differentiability assumptions, the differentiability requirements, but those are pretty easy. As long as you still have 0 over 0, you can keep going. Cool. Let's see what else L'Hopital can do. Okay, so now we're talking about what else we can do with L'Hopital's rule. It's very useful to use L'Hopital's rule when you encounter the indeterminate form 0 over 0. But there are other indeterminate forms. For example, what if you get out the bizarro indeterminate form of infinity over infinity? Whoa, what are we going to do there? Well, there's a version of L'Hopital's rule for that too. Kind of nice. Anytime you encounter an indeterminate form, there's pretty much always a version of L'Hopital's rule for it. Really convenient. So this is the infinity over infinity version of L'Hopital's rule. Here, basically the same situation. We've got f and g both differentiable on an open interval I containing a point A with the bottom function's derivative non-zero on I, except potentially at A itself. If the limit as x goes to A of f of x is positive or negative infinity, and the limit as x goes to A of g of x is positive or negative infinity, then same conclusion, provided the limit on the right exists. Or if you want to classify the way it doesn't exist, is plus or minus infinity. Once again, this still applies if x goes to A is replaced with the one-sided versions of that statement, or with x goes to plus or minus infinity. So this is useful. Basically the same situation as before, just when you get this guy instead of 0 over 0. And really, it's not just this guy. As you can see from these statements right there, from this plus or minus business, really, we can handle all of the following. You can handle infinity over infinity. You can handle minus infinity over infinity, infinity over minus infinity over minus infinity, all the crazy stuff. Any of these guys, every single one of them can be handled by this case. So L'Hopital's rule goes a lot further. We'll see that there are even more advanced versions of it, but for now, let's get some practice with this one. Okay, so we're back and we're going to practice this new version of L'Hopital's rule. Basically the same thing, just able to handle the infinity over infinity indeterminate form. So we're going to evaluate the limit as x goes to infinity of the rational function given by 4x to the third minus 6x squared plus 1 all over 2x to the third minus 10x plus 3. So notice, both these guys, the highest term is something positive times x to the third, right? You got 2x to the third and 4x to the third. As you're going off towards infinity, rest of this stuff, chump change, doesn't even matter. It's just those two terms that matter at all. All right, so as we're going off towards infinity, a big number cubed is still a big positive number. Cool. Both true on the top and the bottom. What we would get if we tried to just naively evaluate this is infinity over infinity. L'Hopital's rule. This is bad. Okay, we got to use L'Hopital's rule. We get the indeterminate form infinity over infinity. The numerator and denominator both approach infinity as x approaches infinity. So we're going to have to really ramp it up. We're going to go way further than we did last time. We're going to apply L'Hopital's rule 3 times. Whoa! Now notice, this isn't really that crazy. When we did end behavior, when we talked about the end behavior of rational functions, we figured out how to address stuff like this. It's not even bad. We just saw that the degree of the polynomial function in the numerator was the same as the degree of the polynomial function in the denominator, which told us that the limit as x goes to infinity would be the ratio of the leading coefficients. So it will be 4 over 2, which is just 2. But L'Hopital's rule will let us get there a slightly different way. It'll confirm once again that L'Hopital's rule is true. Cool. So we notice that this will give us the indeterminate form of infinity over infinity. So we apply L'Hopital's rule. We apply L'Hopital's rule one time there. Take the derivative of the first one, we'll get 12x squared minus 12x, and that 1 just goes away. Take a derivative on the bottom, we'll get 6x squared minus 10, and that 3 just goes away. Once again, a big positive number squared is still a really big positive number. A big positive number squared, still big and positive. Both those leading coefficients, still positive. We have to keep going. L'Hopital's rule, again. Now we derive again, 12x squared minus 12x, take a derivative, 24x minus 12. 6x squared minus 10, take a derivative, 12x. Once again, we still get infinity over infinity when we look at that limit. Yeah? All of these guys still give us infinity over infinity. This is just the ratio of two lines. Take the limit of the top, goes off towards infinity. Limit of the bottom goes towards infinity. All right, one more L'Hopital's rule. 24x minus 12, take a derivative, you get 24. 12x, take a derivative, you get 12. This bad boy right here, we're finally good. There's no x's in there. So the limit as x goes to infinity, doesn't even matter what x is going to. There's no x's in there. It's just 24 over 12. That's 2. Bam. L'Hopital's rule works yet again. Amazing. We'll learn more about the types of situations we can use L'Hopital's rule to address, some much more interesting ones, in our next lesson. Cool. You know, as I've gotten older, I've had a lot of people ask me, why do you do it? The math. What do you do it for? Is it for love? Is it for God, your country, the money, the fame? And I just have to laugh. I just have to laugh because I do math for the same reason that so many brave patriots before me have done math. In hope that maybe someday we'll have the technology to make anime real.
めでとう。